your chat. Your chat. Now you can hear me, I think. Not sure whether you could hear me before. Music is still loud. It's me, okay. There we go. There's my chat. There we go. Hey Tolkisha, hey Sichanet. Nice to see you again. My hair looks terrible. That did not fix it at all. Well, it is how it is. So, how are your Sundays? I'm fine, thanks. Congratulations to your promotion, by the way. Or actually, I should rather say thanks for agreeing to it. No, I'm actually very thankful. Am I in the correct category? Can't remember. By my loyalty or something? I mean, sure. I'm sure you do. Okay. Yeah, I found some funny. Actually, not funny. I found a good Pokemon music playlist on Spotify. Now that's what we are vibing today. I also have some wine. Guided tour, yes. I'm Benjamin, and I will be your guide today. It's basically why why it's in the title. Just because I wanted to say that. Yeah, so I started writing a guide that explains how the library works. Because, well, that's one of the biggest pain points in getting new contributors and people interested in the library, because nobody understands how it works. And so somebody has to sit down and write it up. And, well, that's me. So what we are doing is I'll... I mean, that's what you agreed to, right? No worries, no worries. Everyone's nice here. For now. So what we'll do is... I have a toy example. Not a very difficult or complicated or intricate scene. It's a very simple one, actually, but some things are happening. And... Pika Pika. The joke has layers that you might not understand, and I think it's funny. Cheers. No, I'm not the second born. I am not. Wine time. I see you upped your Twitch emote game quite a bit. Double wine. Og. yeah, so what I'll do is I have a simple example of a scene that's not too intricate or anything, and we'll basically debug that. And that while we go through that, I'll try to remember where I left off writing my article and try to piece everything together. Wait, the music is really loud. At least for me, it is. Is that better for background music? Or should I tune myself down and the music up? Okay. Yo, so let me show you. You just want the music, please. Beamer, can you turn off the camera and just turn up the music? Thank you. Oh, shut up, guys. Shut up. So where are we? Desktop mirror, here we go. I should maybe also think about what to do with the chat, because when I work like that, it's not particularly visible. But well, maybe not a problem for now. Wait, where's my Discord? Whenever I don't see it, it tends to be somewhere, and then I leak a bunch of stuff whenever I go to it. Yeah, would have happened in this case as well. I thought I moved it. Let's put it here. I really have the feeling my Discord sometimes disappears from my screen and just appears on some random other screen that I have. It's weird. Okay. I'll show you the scene, and actually I'll switch to my branch. I have no idea what it was called, so I need to find the... It was 2550. Check out 2550. Your branch is ahead, really? Ah, I remember. So I stopped working on it 2 weeks ago. Probably rather 3 weeks ago, actually. Well. So where's my file? Deep dive is my file. That's this one here. You also can see I've cleaned up the mess that I had with all the staged files, not staged files that I had. Just because I was told so yesterday. But embarrassed by all the people seeing the mess I had in my directory. Well, anyhow. So the current status of this is... Let me see whether we can pull it up. Interesting. Where did this come from? This should go here, and this can go here. So the current status of this is here, in case you want to read along. That's basically the part that goes from the very beginning, when you run from Manim import star to the point where actually the rendering happens. And what we'll do now is, so I think I have to write a bit about object initialization, and then I will actually go and explain the render loop. So the goals for today, more or less, are, I think I'll probably have to do enough with explaining object initialization, because that's actually quite complicated. Anyhow, the example that I'm rendering is this one here. Let me I actually should have that still somewhere. I think I named it, yeah, that's toy. Right, this one. And let's see what happens if I go and render that. rendering. And then we open. So this is it. What happens? We have an orange square, we have a blue circle. We add the orange square in the beginning. The guide goes a bit deep under the hood? Yeah, definitely. It's definitely the thing that goes the furthest into the depths of how things actually connect together that we have at this point. I'm not aware of anything that explains anything in more details. So we play a replacement transform and replace the square. So we turn the square into a circle. We add a dot. The dot gets an updater added, which makes the dot always stay next to the circle. Below the circle, actually. We play the creation of the dot. We animate the shift of the circle. And then we fade everything out. So basically what should happen is square gets turned into circle, dot appears, circle is shifted to the right, and dot moves with the circle, and then in the end everything is faded out simultaneously. Transform, dot, move, fade out. Yeah, and that's our example. That's the example that I want to step through basically and explain how things work exactly. Let me, before we actually start, sorry, I know this is annoying. Let me quickly do some more PR. Because it's not every day that I do this. Shameless retweet. All right. All right. So the current status of the guide was that we explained everything until the point where the library was imported. This is basically this part until here somewhere. And then the creation of the scene object happens. That we also talked about that already. And then scene.render, and I actually wrote this is where the magic happens because, well, I felt like it's true, so why not? All right. I'll throw on the debugger in a moment, and then we'll step through everything actually. What I want to do first, there are two things I want to do first. I got some feedback on this already, which was actually quite reasonable, I think. This here. So Jero said that the variable names should be a bit more self-explanatory. Currently, I think I have S and C and stuff, and that's not particularly good. And I completely agree with that. So we should rename this to orange square, and this should be blue circle. Then this is orange. I could have refactored this properly and let the editor do this, but well, now here we are. Orange square, blue circle. Next to blue circle. Play, blue circle, fade out, blue circle. Is the dot. Ah yeah, right. Let's call it small dot. Because I want to avoid this problem that you have when there's an uppercase class and the lowercase variable. Then I think it's always confusing why change if the variables are named so similarly, then I feel like that might be source of confusion. So I usually like to mix it up with some adjective and make the variable name more explicit. So this is small dot blue circle and small dot. I'm a big fan of long variable names. Yeah, me too in Python especially. Maybe sometimes too long. Well, how's it in Haskell? I guess the variable names are also quite long there. Or maybe choose to make them long. Not really. Okay. So you can see I already set a breakpoint here at the temp config creation. This is the way I usually like to render my examples. And we should now take this code and copy it again to the RST file. Some of you mostly use X and SX as parameter names for recursive operations. Okay, lovely. I'm sure that won't be a problem at any point. All right. So where was I? I've set the breakpoint already, and we'll start debugging this in a moment so that we can step through the actual process of what happens from start to end. I just wanna make the changes that we just made to the variable names to this example file here, because otherwise I will forget, and then, well. Okay, let's see. There is some. I should maybe also check whether there's some sort of RST formatting, highlighting thingy. That's kind of stupid. RST check is not installed. Maybe let's install it. Well, I mean, doesn't seem particularly great. It is what it is. It is what it is. So this is our toy example. And I'll change the variable names here as well again. So, oops, that's not the thing I wanted to copy. That's all this part here goes here again. Oops, that's too far. Yeah, that looks right. SC, SSC, D, D, C, D, C. Perfect. We changed all those. Close again. All right. This was this part here. Then we do it again here. I can just copy this part though. Here, actually, it wouldn't matter because it's just the part that actually renders the video. The temp config is fine. That's okay. It's just the import. That's also fine. That's explaining what we are going through. Do I mention the names of these at some point? Circular initialized and the square is added to the scene. The first frame of the rendered output should thus be an orange square. No, I don't talk about the variable names. That's fine. Okay, there we go. Yo guys, we are starting with the debugging in a moment. The actual render loop step through. from Manim import star. This goes here. That part has been adapted. That's okay. Temp config, render. The command interface and Jupyter notebooks, scene equals 2 examples. Init scene. Okay, I think we got all of the references to variables. There should not be a singular D. Will the guided tour be released on YouTube? I want to make an accompanying video to this thing as well. But primarily the output of what we're doing here now should be the page, which I've posted before. Let me post it again because I see there might be some new people. Copy link. Oh no, that's the wrong one. There is the PR and that's the link. Copy link. In case anybody is wondering, this is the current status of the thing I'm writing up. It basically explains what happens whenever you run the Manim command line command up to the point where the scene object is created, and then the actual interesting part is not yet explained, the part where the render loop starts, and yeah. So that will, I'm working on. That will happen. And please, if anyone has questions at any point, please just let me know. Post in chat. And just ask. Any questions are welcome. Any and all. All right, I think it's time to start. Trollkirche won't ban anyone with stupid questions. There are no stupid questions. I'll make sure of that. I've unmodded Trollkirche already 4 times today, so I'm 3 times today, so I'm not scared of doing it the 4th time. Okay. Okay, sit back everyone, it's time. We start. The thing that I want to go through now is the initialization of the object. So the part that happens when we do this. Orange square equals square. That's the first thing I want to look at in, well, depth. What I'll do is I'll first start my debugger. We'll jump into the thing and we'll walk through everything that happens, and well, we'll see how far I can follow it realistically. At some point, probably we will say, well, okay, this is now like some sort of black box that does the rest. But we'll start with well, digging deeper. Then we'll see how far we can go. All right, debugger, where are you? Can remove all of those. And then we run the current file. Let's go. For some reason, the debugger is always unhappy about the import config line. I have an idea of why that is, but I don't really care about it. We can just step over it. It turns out that's something that only happens during debugging. So we can continue until we reach this point here where the temp config, so this temporary version of the config thing is created. You know what? Actually, let's stop. We should add 2 more options that we should at least work locally with. I should, on the one hand, disable caching, because otherwise we will not see anything. given that I've just compiled this once. And the second, we might also turn on the preview. That should be better. Okay, second try. Now we actually start. Time to debug. Step over. No, actually continue. Okay, we are at the break point. We jump into it. Okay. So at this point, basically this file that you see here is more or less a short summary of what happens when you run the Manim executable that you usually have and that you usually work with. This is how you can use the library as a purely from Python directly as a script, more or less. And what we'll do now is we'll look into what happens step by step. What does temp config actually do? Basically, the temp config command here takes care of the same thing that would happen if I specify some command line options directly as config.something. The advantage of temp config is that it takes your current configuration object, it creates a copy, and it changes some minor the variables that you pass, and then after it's done, it changes it back so that the original config is unchanged. It's quite helpful to do that in case you're rendering several different things. All right, quality medium, quality disable caching through, and preview true. If we just continue with this, then we'll see it will render, and in the end we'll have the video. It will actually also open in case I closed the current version. All right. The part where the scene is created, I've actually already covered in the part of the tutorial that already exists. So we can actually skip over that and head straight into the second part, the scene.render, which is where actually the cool stuff happens. Let's look into it. All right. The first thing that happens when the scene starts rendering is that the scene sets itself up. This has not happened so far. Up to this point, only let's see how I worded it. Up to this point, the scene has only done some initial things that are not really dependent on the configuration. So when the setup is called, in the first stage of rendering, it has to set all of the things that the config directory holds as well. Let's see what that actually is. We'll move into that. In this case, it does nothing. Okay. Setup. Then I was wrong. The setup is just a sort of yeah, I forgot the config stuff already happened. Like the pixel width and height that already happened. Setup is like a hook if in case you have any particular objects or methods or anything that you want to have present at the beginning of the rendering. So you can yourself as a user set up. That's a user facing method actually. Setup one. Right. So you can override it. Yeah, definitely. Just like so the usual pattern the pattern that you usually see in Manim scenes is usually you have exactly this. You have one scene class and you have one construct method that's in there. But actually there are two or three further methods that you could override that do something. One of them is this setup method, which can basically set up your scene. There are some example scenes actually as well that currently still ship with the library, like the linear transformation scene or vector space scene, which basically add like a number plane, a grid on the canvas of the scene before anything else happens. So in this setup phase, you can, if you're doing a video yourself and you have some sort of things that always happen at the beginning of your scene, or some objects that always have to be present there, then you can do this. You can override or just implement this setup method, and it will do its thing. All right. In our case, we have not overwritten this, and we go on. That was easy. GG. And the next thing actually already is this part here. The next thing already is the is that the scene calls its construct method. Let's look at that. We are in our file, we are in our construct method. No, it's override, it's fine. Not override. Probably sounds the same when I say it. Cheers, chat. Okay, so first this custom setup method is called. Second, already the construct method is called. The code now steps line by line through the items you have written in your construct method, and the same thing will happen here. The first thing, and I think this will take us a considerable amount of time, is the orange square. So what we want Manim to do is we want it to generate an orange square. Easy, right? No, actually not easy. What happens if we initialize an orange square? Well, we jump into the init method of square, which is perfectly fine and as expected, right? Given that it's a square, it has an attribute side length which is set. All right, easy, done, no problem. Then it calls the init method, so the initialization method of the corresponding base object, and passes some height and width. The base in this case is a rectangle, so the square asks a rectangle to please initialize itself with the given height and width. We look into that. And the square, so now we are in rectangle, which itself inherits from polygon. The square does that. We are now in the init method of the rectangle. You can see there's some further properties set, like the color and stuff. Actually, if we look at the keyword arguments that we have passed, we still have a fill opacity of 0.5, apparently. That's the thing that we specified here, and also the color. The color is here, that's this orange here. So the color and the fill opacity are still propagated to the constructor of the underlying polygon. Right. Before we go deeper and take a look at what the polygon does and so on and so forth, we assume that if we would continue here, so the polygon is initialized, what exactly does it do? We initialize a polygon with 4 corners, namely up right, up left, and down right, which is exactly the 4 corners of the rectangle. And then, in order to actually get the rectangle of the dimensions that we want, Manim takes the polygon and stretches it. So it stretches it to the given width, which is this call here, and it stretches it to the given height, which is this call here. And then basically, yeah, stuff happens. We'll look at that later. You can make a rectangle have a sort of grid that's inside of it, but that's not relevant right now. We continue deeper. So now we want to look at the polygon. The polygon again is easy. The polygon inherits from polygram, which we'll investigate next, because actually the init method of the polygon just calls the init method of the polygram with the specified vertices, and all of the keyword arguments are passed as well. The one thing that changes here, is up here, vertices is a start list, which means that the vertices argument itself is now a list, and polygram takes a list as the first argument. So we change from passing first corner, first corner, comma, second corner, comma, third corner, comma, fourth corner, to passing one list of all corners. We go on. This is now a polygram. And what the polygram does, it initializes itself, its base class, which is a Vim object, which is actually the part where things get spicy. And then after it has done that, it will do something to actually set its points. So this is the part of Manim where actually points get added to some list. This method in particular. But we're not there yet. We first have to initialize the parent, the so to say the base container for all sort of shapes that we have, which is in this case a Vim object. Vim object is a specialized implementation of the base Mobject class, so it doesn't get further up than that. Mobject is the very last base layer, the last base class that we have. And the Vim object is a special implementation of that. The V stands for vectorized, which means that the data that the vectorized object holds, the points that it has, these points should be connected using Bezier curves. That's basically the idea of Vim object. So Mobject can have points. Nearly on the bottom. We'll see. No, but it doesn't get much further than that, actually. The one thing that's a bit complicated to explain is where do these curves actually come from, and that will take us some time, I suppose. But we'll get there. So now what we do is there are a bunch of properties that this Vim object has that are set and that are either propagated from the default values that it has anyways, or propagated from the values that we specified. You remember we specified the fill opacity and the color. And you will see that actually the fill opacity is 0.5, which is the base fill opacity that we passed at some point. Stroke opacity should be 1, because that's the default value. Stroke opacity is 1. So that's yeah. And then we go on and set a bunch of things. Stroke width, background stroke opacity, background stroke width, sheen factor, sheen direction, close new points. That should be true in this. Wait, what does close new points do? I thought this would be true, because the polygrams should... Well, we'll investigate. I thought this was different, but, well, apparently not. There's something called pre-function handle to anchor scale factor, which I have actually no idea what it really does or is, but maybe we'll find out. Make smooth after applying functions is false. That's, I think, when there is additional smoothing applied to the object. There's no background image, so that should be none. Shade in 3D should be false. Tolerance for point equality. This is something. This is like a machine constant that explains how when there are 2 points, when they are considered to be equal. So if they're sufficiently close, then Manim will start considering points equal. And then there's a parameter which is really, really weird and gives us lots of headache currently, namely the n points per cubic curve, which is the number of points per cubic curve that the vectorized object will have. More about that later. Okay, and after all of these attributes are set, we finally continue to the last layer of objects, the actual base class. So we are now in object. And this sets some further properties. You can set a name to your object in case you want to debug, then you can give these objects an actual name that's easy to read. I've done that several times. There's a dimension which is always 3. I'm not sure why this even is a thing, but dim is always 3 for all practical purposes. Target is none. This is important for animations, which is usually what this move to target mechanism uses, where you have some sort of object in this attribute, and the animation that interpolates between the existing object and the target in some way. So that's also initialized here. There's a Z index. which more or less controls the order of objects on screen, for the Cairo renderer at least. The point hash is set to none. There's a subobjects list. Every object can have several subobjects. The list of updaters is initialized. Updating suspended is set to false. This is a flag that controls whether or not the update functions are run every frame or not. The color is set to either the color that has been passed, which is orange in our case, or none otherwise, if there's no color passed. But I think actually there should be a default value for color, should there? Yeah, white. I'm not sure when that can really happen, that there is none in this case. But whatever. No. So the color is set. I don't want to talk more about that right now. The reset points method is called basically to initialize the object point list. And there's not that much more to say about that. It basically, the object starts out with a one singular point that it has, which is just a 0 vector. So that's why all objects are usually spawn in the middle of the screen, because this is initially set to this 0, 0, 0 in the beginning. This is set, and then we return and run the generate points method. So what this does now is it tells the square, because remember we still have a square. It tells the square to generate its points, and we'll take a look at that. The point initialization for a square actually doesn't happen in this step. It happens later, which is confusing, I admit. But that's Manim. Welcome to Manim. Finally, the last step, the colors are initialized, and that's important again, because basically the fill color. So you remember we only specified the color parameter for the object, and what the difference to this here is basically, or what this init colors thing does is basically it makes sure that these things like the fill, the stroke, and the background stroke, that these are set properly from this one thing that we passed. So we can actually take a look into the fill color method, which basically there's a list of fill colors. We can look into that. The fill RGBAs, and that's this like internal attribute that the colors are actually stored in. Yeah, this is returned. This is returned. And so on and so forth. And that has basically set the fill. It doesn't do anything too exciting at this point, because there's not too much that has to be set. I actually suppose that with recent changes that we've made, that this part could maybe be even removed entirely or reduced in some form, but yeah, that's also Manim. Welcome. This is where we're now actually in the fill method where stuff happens. The color should still be the orange. That's here. Actually still the orange. So it's fine. Yeah. Manim also has a bunch of these methods which touch some of these color arrays in a really weird way, namely by basically there's this fill RGBAs array, but it's not passed. There's one method that gets passed the name of the array, and then everything else happens with some sort of get attribute call. So you can take a look here. The array name is fill RGBAs, and then it gets the array, and here. It sets the array here, sorry, here. It checks whether it already has the attribute, and if not, then it sets the attribute, which is interesting, but well. I'll consider this part for now a black box. I don't want to get into color handling too much at this point. I think it's fine to note that colors are set at some point. So let's go back up, back up, back up. Color initialization done. And this means the object is now fully initialized. And now we go back we go back up into the chain of inheritance and see what else is there left to execute. All right, so we're back in the object is initialized. Now we go back one layer to the vectorized object. The vectorized object, after doing all of these things, only makes sure that the fill color and stroke color attributes are set properly. So this is none in this case because we only passed color, and this has been processed already accordingly. And the stroke color is also none. So these are just skipped. And that already brings us back. So now the vectorized object is initialized. Back to the polygram, which is already a geometric shape. And now we will see how these points of the object are actually set, because that's actually interesting. We have a vertex group. Let's look at this here, maybe. We have exactly one vertex group consisting of the vertices of our polygon. The polygon, remember, was the rectangle or actually the square that we originally wanted to specify to initialize. So you can see the points of the rectangle are 1, 1, 0, minus 1, 1, 0, minus 1, minus 1, 0, and 1, minus 1, 0. That's top right, top left, bottom left, and bottom right. These 4 corners are still passed here. What happens then is we have some sort of first vertex, and the remaining vertices, this is unpacked here. So we have the first vertex is the one top left, and the remaining 4 are in the remaining vertices list. We make sure that everything is a numpy array at this point, because at some point we have to. And then we start a new path. Starting a new path basically involves appending the current point to the point list of an object, which happens here. So this is like a SVG path. Yeah, exactly. Exactly. You'll see that there are some things happening here. So before we started, the self.points list is actually empty. So it's an empty array, the shape is given, but nothing else. Empty list of points. And now what we do to this is we append the existing list and add these new points. And these new points are in this case only this one corner, this top left corner that we just had. So we'll do that. And afterwards we return. And we return again. We've started a new path, which means that we have one singular point in our point list now. Every other point can be added in a different way, namely by adding them as corners. And what are the points that we add as corners? We add the remaining 3 points, which is this part here, where we make sure that every point actually is a numpy array. And then in the end, we add the first vertex again to make sure that the polygon is closed. The add points as corners method is, I think, a bit more intricate again. Let's look at it. The thing that's not so difficult to see, I hope, is what this argument here will be, because that's basically the 3 points and the 3 remaining vertices, so top left, bottom left, and down right, and then the first vertex again. So this is this pair of 4 points, or this tuple of 4 points that gets passed here. Yeah, come on. Okay, now we enter the method. The list comprehension was what just looked a little bit weird. The add points as corners has now, this method has been passed a list of 4 points, or actually a numpy array of 4 points. Wait, no, it's not. It's a list. So the type hint here is already wrong. I expect Manim's type hints are bad in all honesty. There are many wrong ones, and this is already one. So this should be a list of these numpy arrays actually. But well. For every point that's now left, so Python type hints are just for documentation purposes, right? Yeah, exactly. That's why they can be bad and nobody notices until someone tries to read and understand the code, which nobody ever does. Except us right now. The points that have been passed are like the 3 remaining points plus the first vertex again. And now we look at what happens now. Basically, we call the addLine2 method, which tells the vectorized object to make a line from its last point in the from the last point in its array to the next point, to the point that has been specified. And the addLine2 method is tricky because it creates a Bezier curve, a straight line, a Bezier curve that is a straight line from one point to the other. That's what this magic basically here does. And I think this is a good point to... This is maybe a good point to... Maybe look... We'll maybe look at the add cubic Bezier curve 2 thingy here. But then I think we'll consider the rest of it as a black box. The way how this works is a bit weird. It in the end it makes sure that it adds the sufficient number of points to the array. You see, the problem with the points array of vectorized objects is that the points on the entries are not just points that describe the shape, but they are in fact the points that describe the Bezier curves that make up the shape. Which means that there are groups of 4 points in this array, 2 points being the control points and 2 points being the handles. And it always changes between those two types. I think the first one is the control point, then 2 handles, and then again a control point. But it could also be exactly the other way around. This is one major pain point when trying to debug or when trying to learn things. That the points of a vectorized object are actually not the actual points of an object. It's some weird list of points that describe the corresponding Bezier curves. So square would also be stored with Bezier curves. Yeah, definitely. Every shape that you have, every shape that we have, that is a vectorized object is made out of Bezier curves. Everything. That feels strange. It does to some degree. Bezier curves are nice. And the renderer, which we will see in action soon, uses this information in a very direct way. You can set the handles to 0 to get no curve. Yeah. You'll see. You'll see in a moment. So, what does it do? Add cubic Bezier curve 2. And I actually didn't tell the entire truth. So, what it actually does is it segments the points between. Basically, we have a line that we want to draw, and what Manim does with this add line to method is it segments this line into small bits, and then it connects these bits with Bezier curves. In practice, that's useful because while it makes the objects appear larger, so to say, it's useful because it makes some computations easier and transformations look smoother because points are allowed to move a little bit more freely than if the square really just if it just consisted of these 4 corner points and nothing else could move in between, then interpolations between this shape and other shapes would look, well, chunky. In this case, it uses this NPPCC parameter that we talked about earlier, the number of points per cubic curve, to split the object into to split this line between the 2 corner points into smaller line segments. Yeah, right. I'll enter this method so that we can see what sort of information it is passed. But then I think we will consider the rest of it as a black box. So let's take a peek at the add cubic Bezier curve 2 method. Come on. It's still in the expression. Now there we are. So we got this list of points here. We have 2 handles and an anchor. And in our case, the first handle is what? 0.333310, which means that it's slightly to the left of our first point. The second handle is minus a third, 10, which is slightly left of the center of the screen. And the anchor is actually the point on the far left. So these 3 points that are sort of split over this distance between these 2 points is passed here. Yeah, and then stuff happens. So basically, it checks whether a new path has started by counting how many points are already in the list. All coordinates are absolute? Yeah. All coordinates in this case here are absolute. So it checks whether a new path has already started by checking whether the number of points in the points array is already modulo congruent 1 modulo 4, because they should always be in tuples of 4, because 2 handles, 2 control points, and so on and so forth. And yeah, and then it adds this, and then it basically adds this curve as a new Bezier curve. Right, and that's basically the magic. That's basically the magic of it. This was what was required to add this one line segment to actually the points list of the object. As soon as the points list is initialized properly, we will be happy. Let's see. So this continues a little while until all points have been processed. So remember, this was now the first point I think that we saw. So next point is the second one. And it repeats until at some point all of the vertices have been processed and have been set to the points list of the object. Let's actually look at this. Let's look at self.points to get a feeling of how this now looks. The square now has points, and at this point it consists of points indexed from 0 to 16. And you can see the first point is the top right one, 1, 1, 0. The next one is a third, 1, 0. The next one is minus a third, 1, 0. And these actually make up the corresponding Bézier curves between the points. Given that these are just straight lines in this case, the curves on the Bézier curve will also just describe straight lines. And yeah, so that's how the point list in this case looks like. So in the case of squares, the thing I said earlier about the points not actually being points is not true, because in this case the points actually are points on the object. It's just that the handles of the Bézier curve lie by accident also on the curve, because it's straight lines. All right, and then the polygram has been initialized. We can return again. That was the initialization of the polygon. There was nothing else happening there. Squares are accidents. That sounds sort of mean. Yeah, right. And then we have initialized the rectangle and need to stretch it to the desired height and width, which happens here and here. I think in this case nothing happens because we already are done. Yeah, the width is already 2. Let's see whether it does something. I think this was enough and actually quite dense information up to this point. So I think we will consider the rest of this as sort of a black box. Stretch to fit height does the same thing. There is some step where I'm not sure why this is even here. This happens because of this grid stuff here. Yeah, rectangles have some sort of compatibility with grids, but it's not relevant for us right now. Because the grid X step is none, and the grid Y step is also none. So we haven't set these parameters, we don't want to look into that, and these 2 blocks are just skipped. So this actually would be refactored a little to make it slightly more performant in the case that you don't want these grids. Anyhow. Actually, it would have been interesting to see. That would have been interesting to see what Manim does to get the corner points back, because now it has a list of points and doesn't necessarily know the corners of the Bézier curves anymore. It has to step through the points and identify which ones are actually the corner points of the control points of the anchors of the Bézier curves. Well, anyhow, this is skipped, and that's the initialization of the rectangle. And then we're back. So that was the orange square. We have an orange square now. Color was initialized, and the points were initialized. Sort of painful, but well. And now we do it all again for the circle. Oh. in case anyone followed along and listened in. Same song again? Are we looping already? Let me check. Same. Okay. Just okay. Oh, okay. Yeah. I understand. In case anyone has any comments about that, if you read a guide on all of this, what's the information you would like to read? The things I will probably write up are first, custom scene setup method is called. No operation in our case. Then custom scene construct method is called. And this is, well, where the magic happens. Object initialization in depth. Orange square. So what happened with the orange square? Step through initialization hierarchy. Square to rectangle to polygram to polygon, other way around. Polygon to polygram to vmobject to mobject maybe talk a bit about color init. And then what we should definitely mention is how the points are initialized for the objects. Traveling back up until polygram is reached again. Points are actually initialized. And the point initialization, what happened? We had first point added to points list. Start new path. Remaining vertices. And for the remaining vertices, we did what? We added new line segments. At some point, I should mention maybe a short digression representation of points internally. Internal representation of points. Explain that self.points holds anchors and control points, handles of Bezier curves. Yeah, and I think the orange square is not a bad example for that. Because it's somewhat easier than the initialization of the circle. We can actually look at that in a moment if you want. If anyone is interested in this. I mean, I'll do it anyways because I need to get an idea. Yeah, even though I'm mainly talking to Trollkirche here, in case someone else has questions, don't be shy to leave the lurker mode and ask stuff. Let me quickly check something. All right. And let me check a second thing as well. All right. Okay. So we've talked about the initialization of the orange square, which is something. I'll try to write some text later. I don't do that now. It's this session here is mainly for getting an idea of what I actually want to write. I think that makes the most sense. And watching me actually try to write text is probably boring because, I don't know, I get bored while I do that. So why would anyone want to watch that? All right, let's look at the blue circle, which will do more or less the same thing, except that the hierarchies look slightly different. Because obviously the circle is not a polygon, it's a circle. And yeah, we should investigate what that actually means. So let's step into and look at what happens when the circle is initialized. A circle is an arc. And what the circle does, it initializes an arc with the given radius, start angle. In case of circles that are circles that are constructed from arcs, it basically sets the angle of the circle to 2 pi, which is tau. The color is propagated as the color, which is blue in this case. And there are no other keyword arguments, I think. No. So, right, this is processed, and then we go into the initialization of the arc. The radius is not none. We have some sort of radius. Wait, we do have a radius? Our radius was none? What? Really? Ah yeah. Radius float equals none. The next type hint that's wrong. I should maybe fix those while I see them. Oh, type hints in Manim. A never-ending love story. Anyhow, so the radius is apparently none initially, which doesn't matter because it gets set to 1 anyways. The comment here is then also wrong because actually the circle itself passes the radius to be none. Anyhow, welcome to Manim again, everyone. Right, so the radius is set to the radius attribute is set to the past radius, which is at this point 1 and not none anymore. The number of components is interesting because it describes into how many subsegments the circle is divided, and that by default is 9. We have an arc center, which is the origin. The start angle was actually passed from the circle, that's 0, and the angle is 2 pi, so 6.2 something. That's good. I'm not sure what failed to get center does, but we'll find out eventually, I'm sure. I feel silly talking about this. Well, and then we go and initialize the superclass, the corresponding parent class, which in the case of arc is well, not the polygon like in the case of circle before, but it's a so-called tippable V object, which is a vectorized object like before, but it's also tippable. So there is some sort of mechanism that allows, in the case you wanted it, to add arrow tips to the start and the end of the object. Circles don't need it technically, but arcs do, because we have arced arrows. No, you don't say that. We have bended arrows, which basically are an arc with an arrow tip top. Yeah, now all sorts of stuff happens. All sort of stuff happens that has to do with the tips, and none of that is really interesting. The one thing that is interesting is the tippable V object is a child class of V object, and that's the next thing that happens. So some attributes that are relevant for these tips, if they're ever added, are initialized, but other than that, nothing happens. Keyword arguments are still passed on, and I think there should be at least a color. Yes. The color and the fill opacity are still the two keyword arguments that are propagated up to the vectorized object, because the vectorized object is the one that takes care of setting the color correctly. Right, and the rest is actually the same that we've already seen with the rectangle, because now we are at the point where the inheritance structure of the two classes meet. Both are vectorized objects, and the same stuff happens. So I don't really want to go over all of that again, which means I step out again. So the vectorized object is initialized. The underlying object was initialized before that, and now we travel back up. There was one thing I forgot showing, and the one thing I forgot showing is that the generation of the points for the circle actually happens when the object calls the corresponding method, the generating points method. So we have missed the initialization of the points of the circle. As you can see, yeah, you can see here on the left hand side where I watch the value of self.points. I watch the values of the points attributed that there are at this point 32 points that have been added to the circle. So these are now Bézier. These again make up the Bézier curves that form the circle, so to say. And cheers again. All right. Should we go back and look at what happens exactly? No, I don't think so. Just know that the points have been initialized by some logic. Yeah, and then that's basically it again. Points have been initialized, and that's it. So whenever a new object is initialized, it's a good representation actually of what happens currently. Well, the thing you need to know whenever you initialize an object like that is that initialization in pretty much all cases also means that points of the object are computed, and these points describe the Bézier curves that the objects consist of in case of vectorized objects. There are obvious examples where you don't have any Bézier curves involved, and I should maybe take away the plural from that, because the one obvious example that I can think of right now is images. The image object that we have does not consist of Bézier curves because it just is an image that is put on screen. So there you actually read in the pixel array, and then you just throw that into the renderer somehow. We'll soon look at the place where that actually happens. Okay, up to this point, we have two objects whose points and colors have been initialized and set, the orange square and the circle. And the next logical step is that we add, or the next logical step, the next step that happens in our construct method is that the orange square is added to the scene. Let's look at what happens in terms of the code of the scene. So what happens when we actually add something? Let's go. We are now in the scene.add method, which does some things. It first checks, and this is something that pains me a lot. The logic for how our two renderers that the community edition currently supports, the OpenGL renderer on the one hand and the Cairo renderer on the other hand, the logic for how things are added and controlled on within the scene is currently different. So we have several checks throughout the library that look like this. If the renderer is the OpenGL renderer, then do one thing and otherwise do the other thing. That's extremely painful, and a lot of code is actually duplicated because some of these things here are comparable to some of these things that happen down here. So yeah, this is painful. But for now, we will just focus on the Cairo renderer because that's already difficult enough actually. Yeah, the config object is a weird thing, and the renderer attribute is actually a property, so that's why we just went in this method here. We step in, we see that the value of this is actually Cairo because we didn't change it. That's the default value, which means that we skip this part and go into this else part here. All right. Now what happens is the scene forms a list of mobjects, and this list of mobjects consists, on the one hand, of all mobjects that have just been passed. In our case, we just passed the square. So mobjects should be a list that only has the square. Yeah, you can see it here. And then the second part is it adds all of the foreground mobjects of the scene. Foreground mobjects, that's a separate list of mobjects that are always put in the foreground. These are placed last on the scene whenever something is rendered. At some point, I should maybe say a few words about the render loop so that at least you have your pictures in mind. Basically, what the render loop does, in every step, it puts a list of mobjects, namely the list that we are currently building, this list here, self.mobjects. It goes through this list and puts them on the screen one after the other. So at some point there is like a canvas, and we ask the rendering library, Cairo in this case, to draw one object onto the screen, the next object onto the screen, the next object onto the screen in a linearly ordered way. And the foreground objects are like a separate class of objects that are always put on in the very end. So that's what happens. These are the objects that get popped on in the very end. Do foreground objects in itself have an ordering? Yeah. Because everything is ordered. In the end, we don't put multiple objects on the scene, on the screen, on the canvas that the Cairo administers simultaneously. We don't do that. We put one after the other. One object is put after the other. So the foreground objects is there if there's a particular order in that list that will be used that order. Okay. So what happens now? We have created this list of mobjects, and what happens next is the restructure mobject method is called. And fasten your seatbelt. This will be a bit of a ride. I've spent the past like 2 days debugging some weird stuff that happened in these methods, and I still can't really fully wrap my head around them. So let's go. Restructure mobject is called. It gets passed a parameter to remove. And what this does is it unfolds. The first step is it unfolds all of the mobjects that you currently have. What does unfold mean? if you have some object groups in your added to your scene, then this part here, this extract object family members, whenever the code refers of a family, it always means a list of objects with all of its subobjects and the subobjects of the subobjects and so on and so forth. Getting spicy again. Yeah, definitely it's getting spicy. So the family of an object is exactly that, like a full list containing linearly all mobjects, the submobjects, mobjects, the mobjects, submobjects, and so on and so forth. That's the family of a object. So the first thing that happens is it looks at all of the objects in your scene, independent of whether they are wrapped in some other in some other object or not. Let's look at the extract method. There are two different ways. Sometimes we only want those family members with points, so those that are vectorized in some sense, or that have assigned some sort of points. Or we just want OR. In this case, I think we want OR. Yeah, that's the get family part. And now it extracts all of these, basically. I'll step over that and then we'll look at it. Not done yet? Oh, it is done. In our case, this is still very, very simple because our scene has literally nothing in it, and the only thing that we passed to add was the square. So the family that has been extracted at this point is only the square. It then sorts this list according to the set index. And now it gets the list of the corresponding name. You might remember when we called this method, this restructure objects method, we didn't pass a particular object list name. And in that case, it uses the default name, which is mobjects. Lovely construction, by the way. Lovely. Please help with refactoring. So this underscore list here that has been determined is actually the list self.mobjects, which at the initial point of the scene is empty. There are no mobjects yet on our screen, in our scene. So this is an empty list. The new list is, we call the getRestructuredMobjectList method, which we will get into in a moment. Where the first argument is the list of mobjects that we already have in the scene, and the second one is the list that is to remove. And then, well, attributes are set again. And what this getRestructuredMobjectList does is it expands the entire family of mobjects that we currently have in the first list. So this is this one here. And it removes all of the family members that are specified in the toRemove list. So you remember at some point we initially expanded all of the family members of this toRemove list. Now we expand all of the family members of this mobject list, and we remove these out. Why? You might ask. Excellent question. The reason this is so complicated is because Manim tries to make sure that whenever you're adding an object to the scene that is already part, even as some child of some other object, when you're adding it on screen, then it gets removed from this object where it might already be included, and then re-added to the list again. So in case another thing that Manim could actually do would be just check whether it's already included somewhere in the family list, and if it is, then just leave it be and don't do anything. But what Manim actually chooses to do is it removes the item from wherever it is, or the past objects from wherever they are, and reinserts them into the object list, into the very back of the object list. That's what makes this code so complicated. It basically, in simple terms, it looks at all of the objects, all of the sub recursively that you already have in your scene, and it first removes all of them. It first removes all occurrences of the things you want to add, and then it re-adds them separately. That's basically a TLDR of the code that you just saw. Yeah, and then there are some fun things like this inline add save objects from list method, which does exactly that. It steps recursively through the objects and appends all of the ones that are safe and removes those that are not safe. In the end, because we still have a very simple example here, we will find that the new list consists of exactly nothing. Because we didn't have to remove anything from our list. And now we can... Wait, what? Shouldn't there be the square in there? Oh no, the square should have been removed. I'm still slightly confused right now. Let's see. Ah, right. We haven't been in the step yet where things are re-added. That's what confused me right now. We just restructured the objects. So we removed all of the occurrences of the objects that we wanted to add throughout our scene, and now we re-add them in this second line here. Here, now they are re-added, and now the self.objects list actually contains the square. The square has now been added to the scene. The rest of this is a check for a second distinction that we'll encounter later when we actually get into the render loop, where Manim tries to distinguish between static objects. Those are the ones that don't move within an animation and are just painted statically on the screen, and moving objects, which are those that will move or change somehow during an animation or have to be repainted because some object underneath them moves or something like that. So this is the distinction here between moving and static objects that we'll run into later again. Right. I don't want to go into that right now, because actually this is wrong, and this is a bug that I've fixed already and should be merged in the bug fix release that we're preparing. So we can go on with this and return self. Right. So the scene has now been changed in the sense that the scene now has a self.objects list, and in this self.objects list, the square is included. At this point, so this was a fancy way of basically putting the square into the self.objects list. Right. Yeah, that's all that happened, really. It's funny. How long did that take us? 10 minutes at least, I would say. So in the end, the self.add method does nothing but adding the objects that you've passed to it in a more or less safe way to the self.objects list, so to the list of its objects. Let's add this here somewhere. Object initialization of circle, more or less same as orange square. Different inheritance structure, obviously. The next step that happens is the adding a object to the scene. And the thing that was particularly relevant was what? TLDR. Families, which is a recursive list of R objects plus sub-objects of currently already of objects that are in the scene already are expanded. Objects that should be newly added are removed from it and then added safely to avoid duplicates to the list separately. So this mechanism explains that what happens when you have a group of objects that is added to a scene and then you re-add one of the children of the object. The result will be that the child will not be in the parent anymore, but it will actually be separate outside of the scene. I think that's what should happen. It's also possible that something else is happening, but let's deal with that later, maybe. Okay. I don't think I want to say much more about that, actually. I think what I want to do is I want to now start with the next step, which is actually how rendering works. So the next call that will debug is the self.play call. And after we are done with it, I think I want to take a break because this is also quite exhausting for me. And I'm not sure whether I'm doing this basically for myself or whether anyone is still actively listening and tuning in, watching. And I think I wanna start playing games afterwards. So yeah, you are here. I find it interesting. I mean, I like it as well. The one thing that's unfun about it is how complicated everything is to figure out in the first place. So that's well, unfortunate, let's say. But that's also the reason why I think that having this sort of guide, this written up thing, in the end will help bring in new contributors. It's manageable with good docs. Yeah, that's exactly what I think. And currently we don't have that. Okay. Get ready, chat. We are moving in render loop territory. So, in this next line, two different things will happen. The first thing, and that's the thing we'll talk about first, is the construction of the animation itself. First, this replacement transform animation has to be built in some sense, and that means we have to talk about what an animation object actually is, and how it looks like, and what methods it has. So that's what we'll do first, and then as soon as we have that, as soon as we have the built animation object, we'll look into what self.play does, and then we'll get into the actual ugly bits of how the renderer works, how things work, basically. And then we'll do something fun, maybe. I mean, this is fun already. I'm not gonna lie. Okay, let's go. Yo, completely off-topic question before I go. I did mess around with my mic settings a little bit before I started streaming. Is there a noticeable difference to usual, to the other streams? Because if not, then I think that all the settings I touched are basically, well, some arcane stuff that didn't really change anything. So the one thing I try to make sure is that I can. There should be less noise. The sound should be a bit more clear. Maybe it's a bit louder. I'm also talking right into it right now, so I don't know. I'm using different stuff. Okay, well, anyhow. Let's go. We built the animation class, and then the animation object, and then we play the render loop for 3 seconds. Let's go. So what happens in the animation class is that we first run into run into the new method, not into the init method, but in the new method, which happens before, basically. And this has to do with some sort of animation override strategies that we have. Basically, we allow overriding certain animations for certain objects. If you feel like that your particular object should have a different create animation than all other objects, then you can technically override that. And in order to enable this sort of mechanism, this new call here happens. And you can actually see, if we would turn on the debug logger output, that actually tell you that if there is something like that, if there is an override for the particular animation that we're constructing, then it will tell you right now. There is not, so we can actually continue. It should return none, yeah. The function is none, and therefore we are done. So we actually construct the replacement transform now. And there we go. We are in the init method of the replacement transform, and animations in general take a few arguments. One of them is always an object. Animations in Manim are always tied to one object. So if you namely the object that they are animating. Sometimes there are border cases where you might want to play something that affects many objects simultaneously or something like that. But generally speaking, generally speaking, there's always an object that every animation is associated to. And in our case, this is we have an object, we have namely our square, we have a target object, namely our circle, because we want to transform between those two. And the replacement transform is basically just a transform with the keyword argument replace object with target in scene. Rolls right off the tongue. With this one set to true, which basically the replacement transform basically replaces actually the one object with the other, which is useful. And then any other keyword arguments that are passed here. In our case, I think that's the runtime. yeah, the runtime we have specified separately. So that's the replacement transform. We go one layer up to the base class, the transform. Maybe. Yeah, there we go. Transform is inherits from animation, and animation is actually the base class for all animations in Manim, so we don't have to go that much further. And what transforms do is they take the points of one object, they take the points of the other object, and they interpolate, they move the points from one object to the other. To make sure that works, there's a step in between that equalizes the number of points that one object has to the number of points that the other object has. And then all that happens basically is the object is morphed along these points. So you have a starting object, you have a target object. The starting object has some points, the target object has some points, and all that the transform animation does is it constructs intermediate objects in between by moving the points of one object towards the points of the other object along some specified path. In almost all in the default case, this specified path is a straight line, but you could also choose an arc or whatever. That's what happens here. So this path arc axis is usually set to none, I would say. Actually, the axis is set to out, which means that you if you would move it along an arc, then the arc would be in the XY plane. There are path arc centers. In this case, this is none because we didn't specify that, and path arc is also set to, I guess, 0. The exact measure for path arc is I'm not entirely sure what it is, but it doesn't matter right now because we just want this straight line anyways. There's a setter for that, doesn't matter. Path arc centers is not none. No, but it is none in our case, so we don't care. So the path function, that's the function that determines the actual paths along the points move the points move on. So in our case, the path function should be none, and if it is none, it is probably set to the straight line at some point, or the straight line is used in some sense. If it's not none, it's set, but it is none in our case, so it's, well, doesn't need to be set. The replace object with target in scene one comes set to true from the replacement transform, and we do have a target object. And that's it. So the transform animation doesn't do anything else. Some extra fancy stuff that has to do with how the points move from one object to the other, but nothing else really. And everything else is in the base class in animation itself. Yeah, and there we go. There's a type check input method, which I don't even know what it really does. I think it only checks that the object is actually an object. Yeah, so the first argument is actually an object. That's important. That's important because in earlier versions of Manim, you could write the play car in an extremely weird way, where you passed an object, and then as a second argument you passed a method that you wanted to animate. So there was no animate syntax yet, and the play syntax supported different weird kinds of stuff. Basically something like this. You had self.play, then orange square, and it was the method, you passed the method dot shift, and then the argument was like that. This was supported at some point, but we deprecated that in favor of the animate syntax. This doesn't exist anymore. But I think this type check here is still an relic from this time, so to say. The runtime is set. We have specified the runtime to 3 seconds, if you remember correctly. The rate func is none. Actually, it's move. That comes from here. It's the default value. So we set the rate function. There can be a name for the animation as well in case you want easier debugging. I like the new one much better. Yeah, me too, actually. Mobjects, Mobject. I'm still in the Mobject initialization from before. Animations can either be remover animations, which means that at the end of the animation, they remove the Mobject that they animated from the scene. Or they can be introducer animations, which is the exact opposite, which means that at the start of the animation, they add the Mobject to the scene. By default, whenever you're animating a Mobject, any update functions that are attached to the Mobject are suspended. So there's no updating of the Mobject itself, but that comes with a catch. I'll talk about that maybe later, but probably not today. There's a lag ratio, which is set to 0 and doesn't matter in this case. There's a onFinish hook, which is called at the end of the scene. By default, it does nothing, I think. OnFinish is a callable function, and in our case, it doesn't do anything. If config renderer is, and then we are back in the territory where different renderers do different things with stuff. In this case, it wouldn't really be necessary because this is just about the type of base object that is added to the animation if there's no animation, if there's no object passed. There's exactly one animation that I know of, so that might be wrong. There's exactly one animation that doesn't have an object attached, and that's the wait animation. Wait is one good example of an animation that doesn't act on any object. So what Manim does, it adds a fake object to the scene for that one, that acts with that one, basically. And that's happening here. So in case the starting object is initialized as a object, the self.object is either the one that we've passed initially, or otherwise it's also set to an empty object. Right. So empty object is added to self.starting object. And then we are here, and as we have passed a proper object, namely our square as the object the animation is associated with, nothing happens here. This comes from the time when we removed the config dictionary from the community version, and you can still see if there are some additional keyword arguments that are passed to the animation, then it would well, at least lock this here. And throw an error if there is a config dictionary associated somewhere. All right, and that's it basically. So the animation is now initialized. So basically, what did it do? The replacement transform didn't really add anything. It just set this replace object with target in scene flag to true. And everything else was handled by the transform, which only set some information about how exactly the points move from one object to the other, and everything else like the runtime and stuff that was handled by the base animation class. And with that, we have an initialized animation. So what does it store? It stores the starting object, it stores the target object, and it doesn't do anything else really. It has the information about the runtime and about how the points from one object move to the points to the other object. That's about it. Nothing else has happened so far. Which means that now with this constructed replacement transform animation, we should maybe briefly write that up in the thing again. Entering the play car. That's the part we're gonna do next. Constructing the replacement transform. Replacement transform only sets the flag for replacing the object, the starting object with the target object in the scene. And the second part that happened was transform base class has information about how points from starting object move to points to of target object. Animation base class has all other info. Okay, now we enter the play the play car. Let's go. In the beginning, so this is now the scene.play car. This actually plays an animation and writes information. It writes some part of the movie to a file. Eventually. What happens is, first of all, we have a start time, and this start time is obtained from, well, asking the renderer what time the renderer currently thinks it is. The next thing that happens is we pass off the play call to the renderer, because actually the renderer has to do some work now. What I then do is, because the renderer does some work of figuring out what the exact runtime of the animation was. In the end, we get the runtime of everything back, and this only happens because Manim has a subcaption feature where you can add subcaptions to that are written to some separate SRT files, so a subcaption file where you can subcaption your animations. And we need to determine the runtime separately here because the renderer does some things to figure out how long the animation actually was. Then that information is available to us. So the actual interesting part actually happens in the renderer in this call here. This stuff around here is just well, a minor feature for subcaptions. So let's enter the renderer play car. Yeah, now we are in the renderer. In our case, in particular, the Cairo renderer. And we set some things. First of all, we check the original skipping status. Manim has features that allow you to skip through certain parts of the animation. You can pass certain command line arguments that say, well, you want to skip the first few animations and then continue only rendering from animation 17 onwards or stuff like that. And this basically is reflected here. That's what the skipping status basically does. And it updates the skipping state. So first the original skipping status is red, and then the skipping status is updated depending on whether you want to skip this current animation or not. That's not that interesting actually. So this really just reads this information from the config object, whether the last frame should be saved. In that case, we skip rendering all the animation, just want to render the last frame of the scene, or otherwise whether we are in this interval of animations that should currently be rendered. by default, in our case, we want to render everything, so this is pointless. All right, and there we go now. We compile the animation data. So we ask the scene, the renderer asks the scene again to do some work of figuring out stuff about the animations that the renderer should render. This is part of this weird design that Manim have. There's a huge interdependency between the renderer and the scene, and that's bad. We are trying to reduce that, because if you look at the call graph between all of these different objects, it's a huge mess between the renderer and the scene, because they ask each other so many things. That should be cleaned up, and I hope we are doing that at some point. Coupling, yeah, they are tightly coupled. These are tightly coupled, which makes everything extremely complicated, like adding support for a separate renderer, because you kind of need to replicate the sort of coupling currently that the Cairo renderer has with the C, and so on. But again, I don't really want to go into detail with that. I just want to talk about how things currently are, so that we get lots of people that can help to fix this mess. Okay, so the renderer asks the scene to compile the animation data. What does that mean? The animation data, I think the docstring actually gives some information about that. So the scene now gets the list of animations that it passed to the renderer, it gets back, and is asked to determine some things. In particular, it should figure out which objects are static, and which objects have to be painted in every step of the render loop. These are the static and the moving objects. And it should also determine the length of the overall animation. So these are the two things that the renderer wants to know from the scene. One thing, which objects are static, which objects are moving, and then the second thing is the duration time of the. And it does that like this. It assigns an attribute self-dot animations. Why it does that? Don't ask me. It just assigns for one current animation, it assigns an attribute self-dot animations from the self-dot compile animations method. And this method goes here and takes care of whenever you pass animations using the animate syntax. These are not proper animations yet, and they need to be made into proper animation. And I think this is one thing that happens here. Yeah. For every argument in the list of all arguments of this method, these are the animations that are passed. We try to prepare the corresponding animation. And prepare animation is a function which tries to call the build method on these animations in case they are these weird animate syntax things. This here is another reference to the syntax I've mentioned earlier. So if the play method receives a method as an argument, because you could do that earlier, you could say square.shift, and then as a second argument you would pass the argument for the method that should be animated. If it receives a method, the play call, then it warns the user that this is no longer supported. Let's look at this prepare animation function, but it's basically just that. So it checks whether it checks whether the animation is based on animation builder, which is the base class that is used for this animate syntax magic. If it is, then it calls the build method, which actually assembles the animate syntax thing into an actual animation object. Yeah. And that's the third part. If it already is an animation object, then it just is returned like that. We just have one animation, so that would be it. Step over it, there's no exception, it runs through smoothly. Right, and then the second thing that happens, one thing that you might be familiar with is whenever you add multiple keyword arguments to the play core, these keyword arguments get set for all of the animations. So something like this. I'll type something again. Something like this: self.play animation 1, animation 2, runtime equals 42. If you pass this, then basically what happens is that the runtime is 42 keyword argument gets propagated to both of the animations that you've passed in the play core. And this is what happens here. So for all animations, take all items in the remaining keyword arguments that have not been processed yet by the play call itself, which are not very many, and set them by force to all of the animation. In our case, nothing happened, and the animations have been compiled. All right. So this is now stored. The list of animation objects is now stored here in the self.animations attribute. And then what happens next is, remember that I said that Manim knows for all of the animations, they are always tied to some sort of object. The next method call makes sure that all of the objects that you have in your animations are added to the scene. And there is an interesting misconception that has been introduced recently. The animations that are introducers, so like create, fade in, they don't add them objects in this particular step because that's too early. They should only add the objects when the animation actually begins. So right, like in the frame before they start rendering, then they should be added, but not at the point where the animation data is compiled. That's because if you add an animation group where you want to fade in one object after the other, basically, with some sort of lag ratio. Yeah, that was one of the bugs that we had recently. If you have an animation group where one object is faded in after the other, or you want to do that, then if this part would not happen, so if the introducers would add them objects right at this point, all them objects would simply appear on screen, and then probably there would be some flickering before they are actually brought into existence. So that's bad. That's why introducers are handled separately. This part here would take care of adding them object if there is no add call at any point. So for example, if you would call a code segment like this, let's put something up. If you had something like def construct, and then you had self.play transform circle into square, then you would still like to have them objects on screen eventually. And this part of the code that we're looking at right now takes care of that. That at some point, the circle is added to the scene. Should not add the file I'm currently executing. All right, so that's what's happening here basically. I don't really want to go into detail more here, so we'll return from this backup. Next step, the animation is about to begin, and there is one variable that keeps track of the last time step of the animation that has been processed. That's self.last t. There is no stop condition in this case. It's just set to none. And these two special lists, the list of moving map objects and the list of static map objects, is set to empty lists. And then it tries to determine what the scene is actually doing. This first part here queries whether the length of the animations passed is 1 and the animation that has been passed is a wait animation. This here is the case that self.wait has been called, and the scene should actually wait. And then stuff happens here. So this is all of this is responsible for waiting. Otherwise, in case the renderer is not the OpenGL renderer, because the OpenGL renderer doesn't really need this logic of moving and static objects. That's a separate story though. in case of the Kairo renderer, the list of moving objects and static objects is now determined by a call to this method here, get moving and static objects. And what this does is something weird. Actually, not that weird. It can be explained again easily. I'll explain it in words and don't look at the code too much because that gives you a headache. At least for me. The thing it does is there is a list of objects that's currently displayed on the screen, in the scene, right? That's the self.mobjects list. What the code now does is it basically travels through this list, looking at every object that has already been added to the scene, and it tries to decide, because remember the renderer will eventually go through this list and simply put them on top of each other, on top of each other, on top of each other. And it tries to decide which one is the first object that actually moves or that needs to be animated. Because the first object in this list that needs to move, all of the objects above, they need to be redrawn as well every frame. All the objects below this first object that is animated in some sense, all of them below that, those are static. And what the renderer then actually does is it renders a static image containing these first few static objects, and all the other objects are moving objects. So basically it draws a fancy background image consisting of all the objects that do not definitely need to be repainted every time, and everything else is repainted. This is basically what this code here does. It determines the moving objects, it determines the index at which point stuff happens in one of these, and then it updates all of these lists appropriately and returns them and assigns them to these two attributes. I don't want to go into that in detail because I basically looked at this method exclusively for the past 2 days, so that's why I don't really want to talk about it more. That's what it does. There's not really that much more to say about it. Right, and then finally there's an animation. There's a method that is called to determine the runtime of the animation. And to do that, it basically checks the maximum of all the animation runtimes for all the animation, because the longest runtime will be the runtime of the entire play core. And as soon as it has done that, it's done. It has computed all of these things, it has processed all of the things it needed to process, it can return to the play call itself. So this is now back in the renderer. The renderer has asked the scene to determine these values, which objects are static and can be basically in the static background image of the camera, and which objects need to be repainted every frame. That is clear now for the renderer, and it's clear now how long the animations actually last. These two questions have been decided. We are not skipping animations, so this is not interesting. Caching is actually disabled right now, so this will be entered, and so this is the point where Manim's caching system comes into play usually, which basically renders a short, or it looks at the short snippet of code that has been used up to this point in the scene. It hashes that, and whenever it changes, that particular part of the animation is re-rendered, more or less. For us, this is not relevant because we actually want to see what happens when we render. But in case you would re-render and would have caching not disabled, then it would actually not render, because it would just look at, did the code change in your file, and if not, it should just reuse the stuff it has already seen, or that it has already rendered. All right, next step. We ask the file writer. Yeah, we ask the file writer to add a partial movie file, and now things get actually. It actually starts to we actually start rendering at this point soon. starting the partial movie file does what? I'm not entirely sure. It doesn't exist yet, so it makes sure that the corresponding file directory exists where it stores all of the partial animations. And that's, I think, everything that happens here. Yeah. So let's go back up. This prepares the environment for storing the partial movie files. The list of animation hashes gets the current hash appended so that all of these hashes can be saved in the end in the file for FFmpeg to combine. We have a logger output, so it's interesting. And now this is the first part that happens, where actually something gets rendered onto the screen. Manim looks at all of the objects that are static and compiles this background image that the renderer then uses and paints the moving objects on top of it. That happens here in this save static frame data core. For us currently, we only have the square on the screen, and the square is transformed into the circle, so we have no objects that are static. This is an empty image in this case. I'll step over it because it's not that interesting to see what happened in that case. Okay, and now we actually start animating. The file writer the file writer gets called, and the renderer says that the file writer should begin the animation. What does that do? It opens a movie pipe. It asks FFmpeg to listen to the input that Manim will send to it. Basically, we will render frame by frame, so image by image, and FFmpeg will combine these images into one so-called partial movie file. And in the end, after we've rendered all of these separate animations, FFmpeg is called again to merge all of these together to one output in total. So we are not PNG format. The movie pipe is opened and stored for now. Yeah, so this is where all of the config options are actually set. The frame rate, the height and the width, and so on and so forth. All of these, and this is the FFmpeg command that's actually called. It's right here. We should make it customizable at some point, maybe, but I don't want to go into that in detail. Okay. The movie pipeline is open and awaits rendered images. What happens now is the renderer asks the scene again to begin the animation. So what does that mean? All animations have a so-called begin method, and since recently also a so-called setup scene method. The setup scene method would be the place for introducer animations to add them objects. So actually, right when the animation is really about to be rendered, only then the object is added to the scene. In our case, the replacement transform is not an introducer, so this is skipped. And the animation is initialized, or well, actually started, so to say. What this does is it makes sure that the target object and the corresponding copy are created. So that happens here, and the copy is created, so we copy the target. We are not the OpenGL renderer. And this is the method I've been mentioning at some point already. You can remember the square had like, I think 16 points and the circle had like 32 points. This method here makes sure that the data between those two is aligned, which means that the number of points fits together, so that one object, the points of one object can actually move in some way that makes sense to the points of the other object. We can look at this method, but it's actually not, well, it's not that interesting, I feel like. Because there's not that much that happens. And the stuff that happens is rather technical. So basically, points are added and distributed correctly so that this transformation can work out somehow. I'll actually skip talking about it because yeah, there's not that much to say about it. It's aligned so that the transformation works. And the other part that's happening, that's globally for all animations in the begin part, the updating for all objects involved in animation is suspended, so that doesn't interfere with the interpolation of the objects during the animation itself. So the starting object is assigned, then this part here, the object is the updating is suspended. And then I haven't talked about how animations actually work, but basically they have an interpolate method which transforms the object that is attached to the animation into some interpolation between the starting object and the target object. And that's what happens here. Interpolate is called. And that's called and interpolate object calls a method that's called interpolate subobject, which basically interpolates all of the subfamily members of one group into family members of another group, more or less. In that case, it's not exciting because we don't have any groups here, so we can actually return back. This part here, it looks technical, it is a bit technical, but in the end, all that it does is it interpolates the square into something that is between the original starting square and the circle. We've called interpolate with alpha value 0, so that means we are at the very start of the animation, and the square is actually still a square. Right. And that finishes the begin part. So at the end of begin, the animation is basically put into the starting position, where we call by calling interpolate with alpha value of 0. All right. After that, all animations that should be played have been started in some sense. All the objects have been aligned to the starting positions of the animations. And now the renderer checks whether the current animation is a frozen frame animation, in which case it wouldn't have to do anything. It would just take the last rendered output and reuse that. Not the case here. Which brings us from the renderer.playCar back into the scene. Unfortunately, I've said there's a huge interdependency between the renderer and the scene, and this is a very good example for what happens here. We're back in the scene now, and in the so-called play internal method. Let's go. What does the play internal method do? That's the one that actually does the hard work of rendering. Well, actually, that lets the renderer know what the renderer should do next. So we get the duration of the current animations. Remember, this self.animations list has been assigned at some point earlier when compiling the animation data. The time progression is now basically a list of it's basically let's check the method. It's basically a list that tells when which animation is active and when what should happen. So in this case, we only have one animation, which would be the timetable for what happens in this transform animation between start and end. Let's actually look at how this thing looks like. Because then it's easier to understand what I'm talking about. Yeah. It's the thing is a TQD. So this is actually the progress bar that you see when rendering something. It has a description. It's animation 0, the replacement transform, and you can see here that there are 90 steps in this animation, which makes sense because I'm rendering in medium quality, which means with a frame rate of 30 frames per second. And we have a runtime of 3 seconds in total. So there should be 90 steps in total that should be where frames should be rendered. This is what happens here. And then the update to time method is called. This checks how much time has passed, sets the last t, so sets the time, the last time step that has been processed to the current time. And then it steps through all of the animations and lets the objects know, please now modify the points of your objects, interpolate the objects accordingly, so that at the end, when the renderer takes like extracts the current picture from this scene, when the renderer extracts the current frame from this scene, that everything is updated in the way it should be. But that happens here. All the objects of an animation are updated. The alpha value is set accordingly, and the animation interpolate method is called as it should. This part here, I'm not entirely sure what the update object method of an animation does now that I think of it. We might want to check that later. I would assume that it has something to do with update functions. Usually those are called update something, but well, anyhow. So this part here actually calls the update of the this part here is responsible for progressing through the animation. Update objects calls are scene updaters, and update meshes. I'm not sure. I think that's something OpenGL. Update self is again something OpenGL, I think. We can look at it though. So that should be, yeah, that's the scene updaters. This makes the meshes update. I'm not entirely sure. I think that's OpenGL. And this updates self. Interesting. No, sorry. The first one was our object updaters, and the last one was the scene updaters. Now it's correct. Mesh sounds like OpenGL. Yeah, that's why. And that's the update to time method. So basically, there's no renderer involved in that anyways. The only thing that happens is all the points of the objects basically are transformed in some way so that they correspond to the status of the scene after, in our case, 1/30th of a second has passed. That's basically what happened here. We did not skip rendering, but we now ask the renderer to actually render this updated scene, and this happens here. The update frame function is called. And this takes the static image that has been produced beforehand, the ones where all the static objects are on, in our case a black image. And then the pixel, the current background, so that's the black background, which is set to the background of the image, background of the image that is now of the canvas that is now painted, and the actual painting of the canvas happens now here in the camera.capture objects method. This is one of my biggest problems with the OpenGL renderer, with the Cairo renderer. The class that actually does the rendering, that actually takes the picture, is not the renderer, it's the camera. And that's weird. That's extremely weird design and does not really fit to how things are with the OpenGL renderer, where actually the renderer takes the picture again. But it is how it is right now. Actually, the camera should really just, determine the frame, and then the renderer should take care of actually rendering. But for the OpenGL stuff, that's unfortunately not how it is. The camera determines the objects that it should display, in our case the square. Exactly that. It groups them accordingly into groups of the same thing. So basically all vectorized objects are grouped together, objects or images and stuff is grouped together, and so on and so forth. And that's in progressing through the list and taking successive things how long it can do that. So maximum sequences of objects of the same type. Does that, and then it displays them. In our case, we display multiple vectorized objects, which actually gets past the list with only one object, so it will display that. It gets into I don't want to step over it because that's the part of the codebase I'm not that familiar with actually. It steps into the display multiple non-background colored mob. Yeah, exactly. So this is the method that actually does the rendering for the objects, for the Veeam objects. And here the Cairo context is created so that the canvas all of these things are set again. So the pixel width, pixel height, frame, and so on and so forth. I think that's the part where the static background image is loaded onto the canvas. And then, well, actually the things happen. The context has been created, so that the canvas which we paint onto. And then we do exactly that. We step through the points of the vectorized objects. We draw the Bezier curves. And we set color and stroke and everything appropriately. That's these three methods here. The context has been set. We apply the stroke. We apply the fill. We apply the background stroke. We apply the fill, and we apply the actual stroke of the object, of the vectorized objects, and that's it. So this is like hardcore in the center of the renderer, basically. This is the actual interaction with Cairo. After that, the camera has captured the frame. So the frame has been updated. And then the frame is added to the stream of data that is passed to the opened movie pipeline. And that's it, basically. Frame is added, so we add 1 over the frame rate. 1/30th of a second gets added to the runtime. We don't skip. We add that to the number of frames times dt. With number of frames is 1 in our case. Most of the time actually this. I'm not sure why this is even here. And the file writer writes this frame now, so it communicates the information. It communicates the frame that has been, the picture that has been painted onto the Cairo context. It communicates that to the FFmpeg movie pipeline, so that the partial movie file is eventually written. And now we are in the middle of the render loop. So this part here will be repeated over and over and over and over and over again. Frame is written at some point. What is it doing right now? It checked whether we should write to movie. Yeah, here's it. The self.writing process write the frame. So this line here actually writes the frame that we just determined, the frame that just has been updated. This writes the frame to the open FFmpeg process. And that's it. That was one step in this time progression, and now it will repeat that 90 times. So that for every step in the time progression, we write a frame to the movie pipeline. In the end, and after this is done, the animation finishes, is cleaned up from the scene, and the time progression closes. So that's when the progress bar is filled. And maybe let's try to get there somehow. You can see at the bottom of the screen the progress bar moving. This is the 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th frame that's taken. And now we wait until I've done that 90 times. I'm clicking frantically right now. What are the parts of this detour that you would like to read about? So there was some preparation. There was some preparation for the subcaption. Then we went inside of this renderer play car, which asked the scene to prepare animation data, namely the static objects and the moving objects, and the runtime of the animation. Then stuff in the renderer progressed. It opened the video scene. It asked the scene again to begin all of the animations, which adds the objects in case that they are introducers. We are there. We are there. And then basically this render loop here begins, where we step through every time in our time progression and render everything that should be rendered. So the frame is updated according to the time step. Most of the renderer was pretty nice, but maybe less detailed. Yeah, we can do that. I'll take some notes after this one. Right, and that basically concludes the play internal core. So this part here is actually the renderer play call is So the play method of the renderer is the thing that gives you the best idea of how the render flow actually works. The scene compiles the animation data. The FFmpeg pipeline is where is it? The FFmpeg pipeline is opened. The static image that contains all of the objects that don't move at all is added. The animations are started, and then the actual render loop begins. That's basically a TLDR of all the things we've just saw and of all the things that we've just seen. And everything else in our scene actually can be explained by that. So where's our toy example? So this part here, because by now we have seen everything. There is nothing more. All of the things that I've mentioned at some point in this process, they appear somewhere there. This is the 90 iterations that we just finished clicking through. Next, there will be a dot that's initialized. The dot is nothing but a small circle that is filled. We added updater function to the dot, which does nothing except for in the render loop, the scene will update all of the objects according to this. One moment, chat. Yo, back. Where was I? What was I saying? Right. So there's this updater function added, which does nothing except for in the when the render loop is next progressed through, there was this self.add update mobjects command that we had at some point. Where was it? It's in the scene, so we would need to go back there. And all that does is it calls this update function and updates the object accordingly. Nothing else happens. That's all. We play another creation. Animation. We play one of the animate syntax thingies. The only difference to this replacement transform animation is that here the way how the target is determined is a little bit different, and the fact that the this animation object is actually assembled in a separate step in this prepare animations function that we've talked about at some point. Wait is boring because it basically doesn't do anything. And then there's a fade out method which only in the end removes all of the methods again, and that's it. So we have seen the render loop, and there is nothing hidden anymore. All of the mechanisms that occur in the rest of the scene appear there. There is no magic left. That's it. So as soon as we've managed to go through this part here, we've stepped through these 90 frames of the 3 seconds of transformation animation, where in every step the scene asked the objects to update to the corresponding timestamp that was determined that is determined by the animations. And then the renderer takes a picture of that, or in the Kairo renderer's case, the camera takes a picture. But don't forget about that. That's not important. It's bad design, anyways. Yeah, and in the end, as soon as this is finished, the file writer ends the animation, which closes the FFmpeg movie pipeline and actually writes the file. So that's this here, close movie pipe, which closes the writing process and makes Manim output this message that you might have seen before. The info message that the partial movie file has been written. There we go. That's the thing. It's here. Animation has been ended. The number of play cars that the scene has processed so far is increased by 1. And the subcaption magic that I mentioned in the beginning checks whether there's any subcaption should be added, and if not, it just continues. And that's it. So we've seen one entire iteration of what Manim does when you play an animation. First, the corresponding animation object is assembled. In our case, the replacement transform. Well, there was nothing that special about it. Just an object that stores some information about the start object and the target object, and how to interpolate between the two. And then the render loop basically steps through the time progress for that is determined by the frame rate and the length of the animation. It steps through the time progression, and for every time t, the animations I core the objects are updated according to the corresponding animation. So meaning that at half of the time, the interpolate of 0.5 of this replacement transform is called, which updates the corresponding object to something that's exactly in between the orange square and the blue circle. This thing is then on the scene. It's updated. It's captured by the camera. And the image is sent to the FFmpeg movie pipeline. In the end, everything is merged together, and the partial movie file is created. And that's it. And that's it, basically. Wow, now I've talked a lot. I feel like I don't want to really debug the rest of this scene further, because I don't feel like there's too much new things that one would uncover. It's mainly revisiting the things that we already saw and maybe branching out in different parts of it, checking out some parts here and there. But yeah, there you go, chat. There you go. Well, thank you for listening, actually. Do you download your stream VODs? No, I don't, actually. I should have maybe recorded this now that I think of it, but I think I will produce a separate video, a proper one, as soon as I've written up the article. So let's before I stop this and actually play some games, maybe. How late? Almost 7. Yes. So before we change topics and do something entirely different, let's summarize a little bit so that I can remember and maybe start to write something up. What happened after we entered the play car? There was some minor pre-processing regarding animation time for a subcaption feature. Not important. Then we switched from the scene.play to the renderer.play. Inside renderer.play, we do what? We first ask scene to compile animation data, which consists of what? static objects and moving objects plus the animation runtime. Static objects are objects that can be in the static background, that can be rendered once and then remain in the background throughout the entire animation. In terms of layers, ARM objects that are below the first moving / animated object. What happened then? So that's this part here. We compiled the animation data. Then actually what would happen is the caching mechanism takes place. Manim's caching mechanism. No comment. Just say that it is there and allows reusing animations already rendered, animations that did not change. So that's this part here. Then the static background image is rendered. Background image consisting of static objects is rendered. Then the file the movie pipeline is opened. FFmpeg pipeline opens, awaiting frames from renderer. Actually from the file writer. Then the scene starts the animations. Which means that introducers actually add objects to scene. Starting objects are assigned properly. And status of animations animations are set to initial interpolation state. That's kind of cryptic, but I'll know what that means whenever I write that stuff up. Then check whether the current frame is a frozen frame. Whether current animation is frozen frame. Not in our case. Which then switches to the scene play internal. And the scene play internal does what? It There we go. It constructs the time progression. Construct time progression. That is the progress bar. Number of the t values for which frames are rendered. So that happens here first, and then we step through the time progression. Step through time progression. And update, and this stuff here happens. Update to time. Oh, actually, for every animation or for every... Oh, it's actually for the scene. And this guy actually updates the animations to the corresponding time frame. We should say something about it because that's pretty substantial. Update to... Oh, not in the renderer, that's in the scene. So this updates animation objects, runs interpolate for correct timestamp, actually for correct alpha value. And then runs the updater functions. Runs mobject updaters, runs scene updaters. And that's it. So we've progressed through all of that. That's the update to time one, back to the play internal. Yeah, right, that's it. There isn't really anything else. As soon as the time progression is finished, we finish animations. And then we return. I should mention maybe at some point that the renderer actually takes the picture that I have not noticed, that I have not mentioned yet. Where does that happen? Where did it happen? So we had the time progression. I think was this actually here. Self.render. So after updating to time. Actually taking rendering the frame. Okay, so that's basically the render flow. We enter the renderer.play thing. The renderer asks the scene to compile the animation data. Some stuff about the caching mechanism, which is not that important because it doesn't happen in our example. The background image of the renderer is updated, so the static objects are are rendered to the frame. And this background image is basically saved and stored for later. Then the FFmpeg pipeline opens. The scene begin their animations. We actually construct the time progression. We iterate through every step of the time progression and update the objects and animations according to the current timestamp. The updater functions are run, and then the renderer is tasked with taking with actually rendering the frame. So it takes the static background image that we've rendered before, it paints all of the other moving objects onto that, and stores the frame, sends it to the file writer, which passes it to the FFmpeg process that listens in. And this is repeated until every step of the time progression is processed. In the end, the animations are finished, the movie pipeline is closed, the partial movie file is written, and that was the entire animation. FFmpeg movie pipeline closes. Partial movie file is written. And in the end, who combines all of these? At the end, actually, so that's here. After all any animations, combination of all partial movie files to one rendered video. And that's it. So we have explained, or at least I have notes for writing up the entire process of the renderer somehow. Wine time. Cheers, chat. I realize in this very moment that this will be painful to write up. Yeah, this is still a pretty good combination, to be quite honest. It's gonna be a long guide, but I think it will be really, really helpful. And not just for newcomers to the library, it actually will be useful for, well, also current devs. So the thing that would be helpful, the second thing that would be helpful in combination with that would be a guide that explains how the OpenGL renderer exactly works. And then if we combine these two, actually they are not that different. And then we can see what sort of changes and disentanglement we can do more or less painlessly. The thing that really hurts here, and I think that become pretty clear while we walked through that. The thing that became pretty clear while we walked through that is that there's a lot of communication between the scene and the renderer, which actually wouldn't be necessary. So all of these things, preparing the animation data, where is it? The renderer asks the scene to compile the animation data. All of this, I don't feel like this is really necessary. So this could happen before, and the renderer wouldn't have to touch anything after that. But well, yeah, that's a different story. I think it's good that the scene itself handles the time progression and asks the renderer to, hey, now we are here, please take a picture now. I think that sort of idea is not that bad. But that one is not that stable yet, I thought. The OpenGL renderer, it's pretty good actually. There are some improvements. I've recently had a call with Grant, and he said that he has ideas for some of the instabilities that can be fixed. So it's not that bad, I think. All right. I think that summarizes the part. What I will do now is I will try to compile this locally, so that we can maybe have something on the pull request already. So if this would be like an actual list, then it would be much better. I just have to make sure that I get the formatting right, but I think this should work more or less. REST formatting can be a bit weird at times. But I think we can stop the debugging at this point. Where are we? Here. And we can always jump back and to this particular point. And what I actually want to do now is try to render this locally into the documentation and then see whether we can push this and just leave this be for now. I don't want to keep on working on this too much longer. I want to switch to some gaming. Well, yeah, I guess. So yeah, I'm pretty happy with this. We have a rough sketch of what this guide might look like in the end, and that's what I wanted to do for today. Actual writing can be later. We quickly check something. I got an email earlier, but I think it's unrelated. It's fine. Okay, so let me compile this. Look at whether the list actually shows up as a list, which it probably won't, but we can fix that. Make HTML O equals minus T skip Manim. Do your thing. Oh Jesus, okay. We have to make a clean R. I should probably merge the latest main branch into this branch. Before I keep doing anything else. Did we just try that? No, we first render, then we take a look, and then we can still merge the main branch. While this is rendering, we can talk about another question, namely about what games we should play now, because we are more or less finished with Hollow Knight. There's not much more, I think, that I can do. So we could maybe play a run or two of Dead Cells until we think of another good thing that we could... Minesweeper, of course. I don't think my Mac has Minesweeper on it, but there was a website that you mentioned, right? Ugh. We should also fix that at some point. Diamond's Puzzle Collection. I see. Okay, let's check the render page. Open. Build HTML tutorials deep dive. So how does this look? Actually, this is not that bad. I mean, that kind of indentation here is a bit weird. But I think we can fix that. I think what we might have to do is add empty lines here. Whenever we change the level, I think we need a line break in between. That might fix it. I'm not sure though. Re-render. Which ending did you get in Hollow Knight? The normal one. I beat the Hollow Knight. Yeah, lovely. Now this looks like a list. I mean, actually, now that you are here, we could look at Hollow Knight again and collect some of the remaining charms that I wasn't sure where I could find them. I'm still missing out on the final boss. Yes, I don't have the... Was it 1800 essence? If you're talking about that one. For sure. Okay, so this looks like a list now. So what I'll do is I'll commit this. Rough sketch of rest of tutorial. Actual writing still to be done. But rough sketch is good enough for now. Great that we have something. And this typing that we fixed. Wait. I should not change that. I remember. Unstage. No. We revert. Because lots of stuff has changed in this file. Actually, this file doesn't exist in this form anymore. So if I commit the change there, then we have a big problem. I mean, big problem. It's just a one-line change, but still annoying. So let's try git fetch origin main. And idea for some future games would be Loop Hero. I actually have Loop Hero. I played that a fair amount already, but not too much. I can check how many hours I have, but yeah. Git merge origin main. Do your thing. Make clean R. We built the documentation again just to make sure that everything still looks like it should. What a journey through the internals. That was fun. So yeah, I'm not quite sure whether I want to keep playing Hollow Knight for a little bit or whether I should switch to... I mean, I kind of feel like Dead Cell a little bit more right now. But it's basically because, I don't know. I'll probably be terrible in Dead Cells if I play it right now because I've been playing so much Hollow Knight recently. The other option would be Sword and Sanctuary, but I actually don't want to start it today. It's a bit too late for that. Maybe another day. All right, there we go. Does it still look like a list? Yeah. It's fine. So we can push to my branch. And maybe leave a comment. I'll leave the comment later because I might want to link the URL of the VOD of today so that people could take a look if they really wanted to. All right. Anything I missed? Discord in between? No, I didn't. Help question. Yo. Then I guess we start up the game. Is there anything else that I wanted to do? I wanted to prepare the release, but there is still one pull request that needs to be reviewed that I offered, so I can't do anything about it until this is reviewed by anyone. By someone.